video, we're going to discuss, we're going to expand actually on what we've covered in previous videos on fundamentals of C. So we're going to look in more depth about variable types, more about operators, what about expressions. So in this video, we're going to discuss topics like the ASCII convention for representing characters. Also going to discuss in detail about strings because till now we've been dealing mostly with characters, integer numbers, and floating point numbers. But of course, text messages. Which is of course a combination of characters. How do we represent them? How can we create variables which can store a whole series of characters which can be referred to as text, can be implemented in C. Okay, so let's get started. So just a small recap of what we've covered already. So we've looked already at variables, at constants. So we know how to define variables of different types. Constants, how can we create symbolic consistency? So we've looked at that. We've looked at declarations, which is a fundamental concept in C. So before using any variable, you have to first declare it. Now, once you declare any variable, you have operators which can be used to now carry out operations on the variables like multiplication, division. You can do ending, logical ending, and so on. So we're going to look in more detail about that. And then how you combine your operators and your variables. We typically get things called statements or expressions. Yep. So we've already covered these concepts earlier. So this is more recap. Now we've looked at variable naming rules already. So for example, you can start the name of variable by a number. Yep, it should start with a character. Yep, and we can use underscore, as you can see on the second point there. Underscore is considered as a letter, but for example, you can use underscore as shown here. For example, if you want to create a variable for profit June for 2017, so you can use underscore there to make your variables name more readable. So that's something you can do. You can of course start a variable names and underscore, but it's not recommended to do so because in library routines, this is what is used as convention. So you would refrain from doing that, so it will not create a compilation error. Now, uppercase and lowercase letters are different. So for example, here, if you have these three variable names here, num with all lowercase, num with the first letter uppercase, and num with all letters uppercase, they are different variables. So be very careful when you use uppercase and lowercase letters for variable names. It can be quite confusing in a given code if you use the same name but with different case letters. It can be confusing for yourself and for the users of code subsequently to understand what variables you're referring to here. So as we've seen, C practices, you use lowercase for variable names and uppercase for symbolic constants, as we've seen earlier. Again, a small recap of what type of variables we've seen already. So character, integer, float, and double. We've seen that, for example, for integer, we can have signed integer, unsigned integer, long integer, short integer. So you can use these different qualifiers now for an integer, for example, to if you know beforehand what is the range of values for your variable, you can now use this qualifier. This is what is here. So we've used that already. Yep. Now, one function I've mentioned before, but we've not used another size of function. Remember when we started this chapter, this module itself on C programming, we mentioned that the number of bytes, which is actually a reserve for a given variable, is dependent on the machine. So, for example, on my laptop, we might have 4 bytes reserved for integers, but on your own system, it might be 2 or more, so depending on the operating system. So how can we actually find out what is the amount of memory space, what amount of the number of bytes that is reserved for a given variable type? So we can just size of function. So this is a very small piece of code there just to illustrate how it's used. So you can define in a typical program here with your header file and then your main. Now you can define different variables of different types, like this small a is short int, and b is unsigned character, c is float, and d is long double, and x there is an array of floating point numbers. And then you can simply call the size of function to return number of bytes that is actually a reserve for each of these different variables, and use a %d format specifier to represent this number of bytes. The value provided by size of function is an integer. So if you run this short piece of code there, so I'll just illustrate that on my machine how this looks like. Stop this sharing, and then I'm just going to share now a dev C++ environment. So you can see the code there, exactly what I've just shown to you. So if I just run this piece of code there, you would actually get all the different sizes for the different variables. Okay, so important there, you can see the input that is provided to this size of function is actually the variable that you have defined. So for example, short int is a is short int. So when it's the size of a, you're typically finding how many bytes is reserved for a variable of type short int, in this case, which is a. Let's just quickly run this and see what do we get. Okay, I'm just going to share my screen now, my output screen. This is what I'm getting here. So it's the size of integer, which was, if you look at the code we have in the background, so it was a. So your size of a means is 2, is the amount of bytes reserved for a short int is 2, the amount of bytes stored for a character on my machine is 1 byte, for float is 4 bytes, for a long double is 16 bytes. And this was interesting here. We have declared x as an array of 40, of size 40, and it's float. It means the total amount of memory reserved for this whole array x is actually 160. So it means for every floating point number, it's 160 over 40, so 4 bytes is being reserved. So you can see how we can use the size of operator on your specific machine to determine now how many bytes are stored for any type of super interesting function. I would encourage you to just test it through the program, similar program I've just shown to you. Let's get back to the lecture slides. So this is the program which I will encourage you to code and simplify on your machine. The next, we look at ASCII. ASCII stands for the American Standard Code for Information Interchange. Like we discussed before, all the characters, all the numbers just you're inputting in the computer needs to be stored ultimately as bits and bytes, because the computer doesn't understand anything except bits of 0 or 1. Because like we said, the computer is a digital machine, so it's binary. It is using base 2, so it can be either 0 or 1. So what the ASCII code actually, ASCII convention is a system, is a convention that allows us to represent characters. For example, if you input character small a, small b, or capital A, capital B, how these characters are actually stored in the computer. That's what this ASCII convention. It's not the only convention, you have other conventions, but this is usually heavily used in this field. So it's one convention you will come across a lot. So the ASCII is can be represented very simply as a table. So for example, this is half of a table, which is showing numbers from 0 to 127. We know if we have one character is 8 bits. So if you have 8 bits, it means you can represent 256 different characters. Yeah, if it's unsigned, so 2 power 8, it means it's 256. So 0, in this case, 0, as you can see here, the decimal equivalent is 0 here. It means 0 in ASCII, it represents a null character. So similarly here, this is a decimal equivalent. Yeah, so it's an integer number, and it's a character which is represented. So basically, if we go to a character we are more used to, for example, capital A there. So if you represent capital A, if you put capital A in the computer using the ASCII convention, you're going to capital A represented as 65. So similarly, you can find all the different characters here. So uppercase letters from A to Z, and then some other characters which we use, like apostrophe, double inverted commas, the exclamation note, and so on. So it's a full table there, and then small lowercase a to capital to Z is represented from the numbers 97 to 122. Okay, the numbers you find here in hex and octal is simply the conversions of this number to these different hexadecimal and octal. So we won't go into that. Important for us, decimal. So if you display, for example, character A as an integer, it's going to appear as 97 because that's how it is stored in the computer. So just quickly shift to dev C++ just to illustrate this ASCII system. Okay, so I'm going to shift now to a program I've written already, very simple program here. Let me just illustrate what I was showing here. So typical program with the header file stdio.h, because you're going to use a printf and then the main program. And then I'm now declaring a variable c of type int, and I'm assigning 97 to it. And we know Actually, 97, if we consider earlier in the ASCII table, 97 was lowercase a. I'm declaring now a second variable of that character now, and I'm assigning a small capital A to it, so uppercase A. And you can find here, as we've seen earlier, where you when you use characters, it is single inverted commas as here. Yep. So in the first two printf here, I'm simply printing the value of, so let's first consider the small c, which is an integer number. So if we print the uh, integer value of c, because c is an integer itself, so this one is just going to give 97 because the integer you're printing as an integer is going to give 97. In this case now, I'm printing this c there, which is an integer, as a character because we're using the format specified %c. As we've seen the table in the lecture slides, 97 is actually the ASCII representation of small a. So when you represent now 97 as a character, you expect to get small a here. Let's look now at these two other printfs. So in this case, we are dealing with D, which was defined as a character. So in the first printf here, I'm simply printing D as a character itself. So you will get A. This is fine. Now, next printf here, I'm printing the integer equivalent of the character variable D. So I'm using the format specifier %D. So you expect here to get 65. Remember the table we've seen, capital A is represented as the integer number 65. So just quickly compile this and run. So I'm just going to share the output screen with you a few minutes. It's just still compiling, running. Okay, let me just share the screen with you, output screen. So this is what I'm getting. So if I just show you the code in the background, so integer value for C is 97. This one is integer 97, but the character equivalent of it is small letter a, as I've seen. This was in the ASCII table. Now, what about D? D is a small capital uppercase A. So capital letter A. So if you print C or D as a character itself, you get capital A. But it's interesting now if you were to print capital A as an integer number, you see the ASCII representation is going to be 65. Yep, so this is what you find in the ASCII table. So I'm just going to show that again to you. So in the code we've just looked at, basically we've done two things. We first declared a variable which is an integer variable assigned to 97, and we've seen when you print the character equivalent, it is small a. That's what you see there. 97 is the representation for small a, and similarly 65 is for capital A. See what you just see. So you can play around with that, printing integers as a character and character integer. You should be able to get what you find in this table here. Now, you have other characters which can be represented. So in this case, it was half of it from 0 to 127. You do have some numbers which are not used till now. Yep, if you look at this table there were numbers like 143, 144. So you have the whole set there of table, but there are some characters which are not used. Like 55, you see it's not allocated yet. Okay, so these are special characters which now can be used because we have 256 possible combinations. So this table we find here is what the ASCII convention declares. You might have other conventions which assign other characters to this whole character map from 0 to 55. So let's come to strings now. So remember when we started this module, we've displayed hello world on the screen, and it was just printing hello world in the printf. But now we have not been able to, we haven't looked at means to store this hello world in a variable. So here, if you want to do that, we refer to this variable type as a string. So till now we know how to store a character in a variable. So we can use a character variable. But what if you want to store a whole series of characters, which is referred to as string or text in a variable? So we would need to use a different variable type, but it is something which you have already come across. We're going to use an array. So an array of characters is a string. So we know how to use arrays already. We've done it with floating point numbers, integers before, and we know how to deal with characters. So if you combine the two now, means you have an array of characters. I showed here, for example, if you use such a syntax there, character greeting. So the 6 there, the size of your character array. And then, as we know, every element of a character needs to be single inverted commas, as you can find here. This is one way you can use to declare string, but it's not very easy to do that. You have lots of things to type, as you can see here, and what you find here at the end will come back to that in a few minutes, a null character. So a more convenient way for you to do that would be to use this syntax there, which is exactly the same here. So you can see in the square brackets here, we don't need to include the size in this case, because as we've seen for other arrays as well, when you are declaring and define at the same time, the compiler can find out what size it is. So you could include a 6 there, or you can omit it. Now, if you declare it in this way, if you are treating the greeting directly as a string, you use double inverted commas now, instead of having each individual term in single inverted commas, because these are characters. So it's a string of an array of characters, string of characters. And then here we are combining all this together, and then you have a single double inverted comma. So this is more convenient here. So this is how the string, the array characters is actually stored, very similar to what we've seen for arrays of numbers. So each element is actually having its own index. So this first index is for the first character, second index. So we know indexes start at 0 in C. So if you want, if you call the string there, for example, str, if you call this str, or in this case we've mentioned it is greeting. So greeting 0 in this case would be greeting square bracket 0 will be capital H, greeting square brackets 1 index is going to be E, and so on. You can also clearly see that here. So this is the index 0, index 1, 2, 3, 4. Now let's talk about the null character. Now all string text ends with a null character. See, so this is how the compiler would know that your string is ending. Yeah, so when you're typing any string, say hello world, for the compiler to know that, or any functions which you're using, which is operating on strings, we need to know what stops, because in memory, you have to be careful. In memory, it is a continuous. Your memory in your computer, your laptop is not restricted. It's not ending somewhere. It's a continuous map of addresses. So using the null character in C, the compiler would know where to stop, where the string stops. So typically, if you type something like this character greeting hello, automatically the compiler would append the null character at the end. This is what you find in this case here. So you can explicitly do it like this. If you don't do it, if you do it like this, the compiler would append the null character at the end. And as you can see, every location you have here. So this one we know is 1 character, so it's going to be 1 byte typically, and every element of your string, of your array, is going to have its individual addresses. So this is hex, as you can find here, hex. Okay, so based on what you've discussed here, you can start playing around with programs like this now. Yep, so you use the character and then array to create a string. That's fine. Okay, so a small exercise for you. So write a program which determines the length of a string. So once you've defined a string in this way, or using this type of syntax, how can you find its length? So basically, you can scan through your string until you reach a null character. So you could be incrementing a counter, for example. You start your counter at 0, and then for every character which is not null, you just increment this counter. So you start at 0, and then when you get this one, it becomes 1, 2, 3, 4, 5, and then when you reach the null character, then stop incrementing the counters. It could be done very easily in a while loop. So very interesting exercise for you to try. So the program should request a use of a string of a given maximum length and determine the length of a string and display the value. Okay, so it's something which you can work with. Okay, now some functions which are already provided to you in this environment in the string.h function, string.h header file, string copy, string cat, string length. So remember in the program just discussed with you, it was about calculating the length of a string, which I will encourage you to do, but you already have a function called str length. So if you pass any string to it, it's going to return its length. Yeah, so you could write your own code and then use string length and compare it to how it's working. So all these functions you find here will be string.h, string.h header file. Another function which can use is string compare. Yeah, so if you go to compare two strings, let's see this one, what are the different possibilities as output from this function. So if when you compare two strings, S1 and S2, if both are the same, so if you say str, let's say S1 is hello world and S2 is also hello world, so you're comparing two strings which are exactly the same, the outcome of this function will be 0. If when you compare the two now, you get S1 is less than S2, you get a negative number. If S1 is more than S2, you get a positive number. So you'll be asking yourself, how can we decide if two strings are equal? That's fine, all the characters are the same, but how can we set one string is less than another one and one string is more than another one? It simply relates to the ASCII code. We just look at each of the elements you have in your string, in your text, in your array is actually represented as a number, integer number. So when you're comparing two strings, the string str compare function would start with the first character in either case. If when you compare the two, they're different. Yeah, if when you compare S1 with S2, they are different. So immediately you would not get 0, you will get either -1, a negative number, or positive number. And then depending on whether the first character that you have in S1 has an ASCII value which is more than S2, then it's going to be this case here. If the integer equivalent of the first character in H is less, then you get this condition. If they are both the same, yeah, if they are both the same, then you get a condition where it's going to check the next one now, the second character. If they're still the same, compare the next one. So it's going to keep doing that. If after checking everything, it is all equal to the same, so it's going to be 0. If at any point in time there's a difference between any two characters and the corresponding indexes in your array, then it's just going to compare the integer equivalent of this character, and then you have two conditions. It's quite straightforward to look at. So at this point, I was just going to shift to dev C++ to just illustrate these different possibilities and encourage you to write. So as you can see here, you have the string.h header file which has been added. st.h we already use a lot. So let's look at these different lines. So here I'm just declaring a character array of size 30, and I'm not initializing at all till now. Whereas for greeting, this is what we've seen in the slides. I'm already declaring and also defining it, assigning a number. We have two integers defined here as I0 and num0. So basically, this could be used for the string length, for example. If you run a piece of code like this, printf length of string. So if you want to calculate the length of the string greeting, so it's going to be 0, 1, 2, 3, 4, 5. Yep. So you will get. Let's just try to run this and see what we get for the first one. So length of string greeting, and we see this has assigned with a null character at the end. Compile. Yeah, so saying length of string is 5. You can see here, I'm just going to share the upper screen with you. This is what we get. Length of string is 5. Then we have the code continues. We're going to look at that in a few minutes. So length of string is 5. So if you look at our code back, yep. So you can see here the length of string is actually 1, 2, 3, 4, 5. So null character is not taken as part of your length of string because null character is appended at the end automatically. It's not counted as a length, but the size of the array has to be one more to accommodate this length. Okay. Now let's look at the other things. If you wanted to use, for example, scanf to get a message or text from a user, you can use the same syntax, but with the %s format specified for string now. And you can see your str was actually defined as an array of characters. So you can request now a string from a user, but you'll find when you use the syntax there, if a user inputs a text with blank spaces, with spaces in between, it's just going to take the first part of it. Whenever you press the space character, is going to stop recording that. So if you want to actually take messages with spaces, you would have to use this small wildcard there. The same thing, %s, but you have to include this, what you have in square brackets. So this is basically saying here, take characters until you press the enter button of the space button. Yeah. So if you want to write, for example, UOM is actually true, for example, so between UOM and is, you have a space. So you don't want to stop reading the characters when you press the space. So if you use such a syntax, it's going to do that. So it's going to take UM, it's going to omit everything that is after the space. If you want to still take the spaces, the blank spaces, when you press the space bar, you would have to add this wildcard there. So I would encourage you to just do that. This part of the code there, which you find, which is commented here, is what I mentioned earlier to find the length of a string. So I would encourage you to work on that. Okay, this part of the code here is calling the string compare function. The string compare allows you to compare two strings, and like we said, it's going to give 0, negative number, positive number, depending on which one is greater. Now you have a very interesting function called string cat. String cat is for string concatenation. Concatenation simply just put one string after the other one. So it's going to take, for example, if you have one string which is the second string which is is. So if you want to add and then is, you can concatenate the two strings together. So I would encourage you to use that. So this one seems a bit complicated here where we are having nested functions there, but just use a simple thing like string cat, string, and then a blank space, and see what happens. So for example, if you have got your greeting hello, and then you have a second string, as let's say a second string for world, if you string cat the first string and the second string, then you can put both together. You can append one after another. That's what this string cat does. Okay, so I would encourage you to just play around with these functions. Okay, so I'm going back to slides now. Okay, so we look at the string compare. So the string cat is what's here. You see what I mentioned. So string cat concatenate. So add one string after another. So if you put S1, S2 basically takes what is in S2 is going to put it at the end of S1. Okay, so you to use these functions. The arithmetic operators is quite straightforward. We've discussed that a lot. We've used them a lot, like plus, minus, multiplication, division. We've also used a modulus operator, very useful. Remember when we were when we wanted to find what the integer number is an even number or odd number, we've used that. So we've used a percentage operator before. We've used the relational operators as well. So greater than or equal to, less than or equal to, and then this one is actually checking if two numbers are equal or checking if two numbers are not equal. So it's very different result to using a single equal to. Yeah. Single equal to for assigning, this is for comparing. Now, the double ampersand is for, as you can see here, double ampersand, not to be confused with the single ampersand used for address of variables. We'll come to a video on pointers soon where we use the single ampersand, but the single ampersand in this case is for logical bitwise operations. We're going to see in a few minutes. Now, if you use double ampersand or double this symbol there, it means this one is a logical and it's a logical or, yeah, as we've learned it in binary logic. Okay. Now, next, let's look at the increment and decrement operators. Again, we've worked with them already. So the increment operator is plus plus, so it's going to add one. Decrement is going to subtract one. Now, you do have the prefix and the postfix. So this one and this one, in some cases, doesn't matter which one you use, but in other cases, it does. Let's take an example. Let's say as part of your code, you have something like this. X is equal to n plus plus. So what is going to happen here? It matters if you put plus plus n or n plus plus. So what's happening here is if you have x equal to n plus plus, it's going to first assign the value of n to x and then increment n, and the new value of n would not be assigned to x. So let's take an example. If let's say your n was initially 5. So if you say x equal to n plus plus, the value of 5 would first be stored in x, and then n would get a value of 6 afterwards. So this is very different. Whereas this one we're saying here, increment first and then assign it to x. So in this case, if your n was 5 initially, the value would first be incremented to 6, and then x will get 5. So this is it's going to have different outcomes in this case. But in cases like when you use the increment operator in the for loop, for example, it doesn't matter which one you use. Now, bitwise operators. You can see here bitwise operators. You have the ampersand, you just got the ampersand and the operator. Okay, and this one is a bitwise exclusive or, and this one is a left shift, right shift, and the ones complement. Now let's look at what these things means. Let's look at the first one. The first one is bitwise AND. So there's a very big difference between the bitwise AND and the logical AND we've seen earlier. So logical AND is going to treat the number as either true or false. Now, what is true and false in C? Anything which is 0 is false. Anything which is not 0, be it negative or positive, is going to be true in C. So when you use a double ampersand operators, it's just treating the whole number as a true or false. So for example, if I just write something here, if you say a number 1 and so the double ampersand here earlier and 2, the result of this would be, because 1 is true and 2 is true. So when you say true and true, you get true. Yeah. On the other hand, if I say, let's say 100 double ampersand. So again, the logical AND 0. So 100 is true, 0 is false. So we know true and false is going to be false based on what we got earlier. Now, when we are saying bitwise AND, it's not dealing with true or false here. It's actually dealing with the digital equivalent. So for example, if you say 1 and 2 here, we know 1 is 0, 1. And the 2, we know is 1, 0. So it's going on a bit level. So it's going to end bit by bit. So 1 and 0 is 0. And 0 and 1 is also 0. So the result of this is going to be equal to 0. So if we do like this, 1 single ampersand 2, the result would be equal to 0. This is bitwise operations. So same comment for this one. For all, so if you use bitwise all, it's going to deal at a bit level. If you use, for example, this one, same thing. Now, left shift and right shift is simply shifting the bits left or right. So if, for example, if you want to shift your bits left, if you have, let's say, a 1 and you want to shift your bits left, so 1 we know is 0, 1. Now, if you shift it left, you have now 0, 1, 0. Because when you shift to left, this was at this position, you are shifting it left, and then you'd have to insert a 0 on the right. Yeah. Now let's see what's happening here. So this one actually is a number 1. This is a number 2. So when you do left shift of one place, we find that the numbers multiply by 2. So if you keep shifting now one more, so this one's going to come here, and then you have to add 2 zeros, and then this 0 will be here. So you can find this is 4. So you can see when you do a left shift, you actually multiply by 2. Right shift, same way you find that now when you start right shifting this one, you will totally lose this 1. It's going to go out and you get 0. For example, if you right shift this one, then you will get this one. So it's the opposite now. When you do right shifting, you're actually dividing by 2. One's complement is simply inverting the bits. So if you have, let's say, a number like 0, 1, 0, 0 here, and you do a one's complement, so you're inverting all the bits, it's going to become 1, 0, 1, 1. Okay, so I would encourage you to again play around with these different operations here and going. So play around with these different operations. So these are bitwise operations, very important, and the double ampersand and the double operation we've seen earlier are at a high level where we're dealing with either true or false. Okay. Now we've seen these different constructs here as ASCII operators. So instead of writing I equal to I plus 2, you can simply combine this with this equal to and the plus and say plus equals to. So we've seen that, and you can do a very similar thing with different operations. So for minus, multiplication, and even the left shift, right shift, the bitwise operations, you can use this type of construct. Okay, so this slide is simply showing a short form to write. So if you had a situation where you want to set the value of Z, depending on a comparison here. So this is totally a valid C code, but a more compact way to write it is in this way here. So let's look at that. You're comparing A and B. So that's just a comparison. That's the outcome you are using to decide whether Z is this value or this value. So Z is equal to, and then you say A is greater than B. That's the comparison you have there. And then the outcome, if this is true, it will be A. So you put the A there. If it's false, it's B. And then you have the question mark and then the column there. And of course, semicolon at the end. So this is another way to write this one, a more compact way. So you might use this one or this one, depending on your preference. In a piece of code, if you come across something like this, then you have to be aware that simply we are having a comparison here. We're doing a checking of this is a condition. If this is true, then Z is given value of A. If not B, of course, it doesn't need to be A and B here, it can be anything else. Yeah, depending on what you want Z to be, if this is true or what is false. Okay, so I'm stopping this video here, which was on characters, on expressions, and we look at strings, very interesting. We look at some functions you can apply on strings. We look at ASCII convention to represent characters, and we've seen the bitwise operations, which I would encourage you to look at. We're going to come to that in the lab sessions we're going to have. Okay, thank you very much.